All right, let's get started. All right. If you take a look at the handout, it might seem like a lot of slides, but that was just the purpose of reference, I think, because we are not going to go through all of them. And because this is the last lecture and the final is approaching, spending a lot of time in the last lecture will be, well, not a very good strategy because it may be sort of so close to the final exam date and you won't have enough time to prepare for this. So I have already decided that there will be only two problems that will talk about magnetic field. And what I'm going to sort of talk about today will be not exactly, but it will be the topic that is that are going to be included in the final. Okay, sounds good. So you don't have to spend too much time studying the whole subject or the whole topics and just only, face just a portion of the whole thing in the final paper. All right, so I will stress exactly which part that's supposed to be on the final paper and which part I'm just sort of talk about the principle or the theory that's supposed to be sort of incorporate into into the final result. Okay, so that will be, I think, the most efficient way of getting through this magnetic field topic. All right, let's go through it. So what we are about to do, it will be pretty much equivalent to the electric field, but what we are about to do here we call magnetic. That's another kind of natural force that we have to deal with. We already had the charge, okay, and we know that every time you have charges around their area will be electric field coming out in case of the positive charge, and there will be electric field going towards it if it's a negative charge, right? However, there is another kind of force that sort of we can detect in our nature, and we named it magnetic. Okay, so we're going to use the same concept of field. So there will be another type of field due to the magnetic source. So we had the charges to be the source of the electric field. What we will learn today is what kind of source that is going to generate the magnetic field. If you see the equivalence between the two sources, then the rest of the concept about fields will be about the same. Okay, but the complication comes in. It turns out when you have particle in magnetic field, it will behave differently from the charge in the electric field. All right, and that's the key of the discussion today. That's one of the key. All right, so this is pretty much the first thing that's supposed to be, we are about to be focusing on this topic, and this is going to be the question in the exam. All right, and the second one is the law that helps you evaluate the field. And I already picked the law that actually make it quite easy to calculate the magnetic fields. We call the Ampere's law. But you will see toward the end of the lecture that it turns out the formula or the result that you get from this is very simple. So what you really need to take into the final exam room is just the result. Right? So once again, even though you don't understand the derivation of the whole thing very deeply, you should still be able to apply this law and apply the results to solve the problems in the exam. Okay, sounds cool? All right, so these are the two main things that you're supposed to focus on. That's it. All right, and the rest will be something that accompanying these two. Okay, so let's get right to it. All right, so the source of the magnetic field that you can find in nature is just magnets. All right, okay, and of course, back in the day, people don't know what actually made up of the magnet. All right, but now we actually know because we know the atomic structure of material, so we know what's inside those magnets. All right, but anyway, let's think about the magnet to be the source of our magnetic field. So that means around these magnets you have magnetic field. The only problems that you have to deal with in this case is it turns out you never find the magnet having only single pole. When you say single pole, actually the pole is equivalent to the polarity in the charge. Okay, it sort of indicates that there are polarity. So that is equivalent to the charge that having a positive and negative charge. In the magnet, we're going to call they have two poles that we named it north and south, all right, because a historic reason due to the navigation system and all this stuff, we rely on this kind of magnetic field. So that's why we have two types of the pole as well, the polarity of this. Actually, there are two types. We call them north and south. So this is equivalent to the positive and negative in the charge. Okay. Now, the thing that I said that this is sort of different from the charge is because you never, well, we haven't seen one. You never had a material or particle or whatever matter have a single pole. So that means it seems like in this universe, there's no monopole. Unlike charge, you have positive charge, that's fine, like proton. You have negative charge, like electrons. You can have like just a single charge with a single polarity, positive or negative, you can pick. But in the magnet and the magnetic business, you cannot. Whenever you grab south pole of a magnet, the south will always follow with it. So that means it's always come in pair. Okay, north and south. Even though you have a magnet bar and then you slice it in half, each half will compose of north and south no matter what. And you can keep slicing in half no matter how many times, you're going to end up with north and south side by side all the time. Okay, and this give you a final result of, well, we use the same concept of fields, right? So we're going to use the same sort of agreement and convention that if you have a north magnetic field will shooting out from the north pole of the magnet. So that means there will be magnetic field coming out from the north pole, coming out, just the same as the positive charge having electric field coming out of it. And for the south pole, the magnetic field will just pointing towards it, just like the negative charge in the electric field. However, because north and south are always together, so that means these lines that coming out from the north eventually will have to find its way back to the south. You guys with me? All right, this is very close to when you had a condition of positive and negative charge next to each other. The electric field will look like a loop. Same thing over here, but this one seems like it's a like sort of like it's a restriction. You always get like a loop type magnetic field because north and south always side by side. So that's why I look at the figure on the right. So this is what happened. In general, there will be magnetic field that like a loop all the time around any magnet. Even the Earth, because we know that every time we have a compass, the compass always pointing north. Okay, that means the north pole of the Earth actually is going to be the magnetic south pole of the Earth, right? So that's mean in terms of the location, right? The north portion of the Earth is actually the south pole of the Earth magnet. Okay, so that means the geographic north is the magnetic south for our Earth. Okay, something like that. All right. But anyway, the key point of this one is the shape of the magnetic field always come in like a loop, something like this. Okay. All right. But it doesn't have to be always, but at least every time that you look at like big picture, the north and the south always side by side. So the magnetic field always sort of come in a loop. But of course, if you're focusing on just a portion of this magnetic field, you can still have the magnetic field that looks pretty uniform if you want to. Right? So that is fine. But at least in the big picture, you always have the magnetic field come in the loop. All right, so this is just give you like a grand overview of what does it means by the magnets generating magnetic field. But because the magnets always have north and south pole next to each other all the time, so the field that's around any magnet will always come in the shape of a loop all the time. All right. Okay, but anyway, we're going to still look at the concept of the force within the magnetic field. So we can still use the same sort of like agreement or convention that if you bring the bar magnets with the different polarity, okay, so take the North Pole next to the South Pole, they're going to apply, they're going to receive the attractive force. So this is the same agreement when you have positive and negative charge. So we still use the same convention. And same thing with this, okay, south and north attract. And when you have the same type of polarity next to each other, it will repel. Okay, so we use the same sort of the convention like in the case of electric charges. Okay, sounds good? All right, but anyway, because of the complication of some things that generating magnetic fields, and when the charged particle is in the magnetic field, that is a funny business. It's not as easy as the case of the electric field. So that's why what we're going to focus on is we're going to still use the same idea, okay, and we're going to start from something super simple first. Even though everyone knows that if you have a magnetic field and you put the compass between, I mean, in the field, the compass will try to line up with the magnetic field. This one is like a known property, but actually rotation of those compass due to the magnetic field is something that you have to sort of like, come in with well, it's not an easy task to calculate actually. You have to calculate what is happening to those compass in the magnetic field. So that's why we have to first learn what is happening to the particle in the magnetic field first before you will eventually know why the compass behave that way. All right. So that's something that we're going to start with. So here we go. So we're going to start very simply by looking at a particle in the magnetic field. So let me give you an idea first. Back in the day of the electric field, when you have a charged particle inside the electric field, right, if you guys remember this, yeah, okay, you said that, Ajahn, the force that acting on this charge is simply just the charge times the field, right? This one is like, okay, then this one is just exactly what we had with the gravitational field. When you have the mass in the gravitational field, you feel the weight, mg. When you have the charge in the electric field, you feel the force, q times e. What about the magnetic field? It turns out it's not the same, okay? So that's why this is the first complications that comes in. Okay, let's stick with me here. So it turns out we're going to have some sort of like a requirement for the particle to feel the force, or well, sort of like officially it means there will be a magnetic force acting on the particle. You have to have these conditions required. Okay, hello. Hi. All right, we have visitor now. All right. Okay, just take any seats that you like. Okay. All right, just feel free to spread around. Okay, welcome. All right. So we are about to get to the particle in the magnetic field. All right. Okay. First time seeing your face right now. Oh, yeah, your second time. Right, right. Yeah. Forgot about that before the midterm. All right. Very good. All right. So what we are about to do right now is what's happening to the particle in the magnetic field. So the key concepts that we're going to try to get to is to calculate the force once again. All right. But how can we calculate that force when it's not simply just the product between the charge in the field anymore? Okay. So the requirement is the following. First, of course, you need a charge. Okay. Because if you have a neutral particle, it won't experience anything. Okay. Because the neutral particle won't receive any electric field, don't receive any electric force. It's not going to get any magnetic force. It's get nothing pretty much. So you need to be charged up that particle. So that particle must come with a charge. That's the first requirement. Second thing, this is new. That particle need to move. So you need some velocity. So not only the charge, but that charge has to move in the magnetic field for that particle to experience the force. Okay, and of course, we use the character B, okay, for representing the magnetic field. So electric field, we use the E the magnetic field, we use the B. All right, so of course there will be magnetic field. So the size of the B will tell you the strength of the magnetic field. Okay, that's no big deal. All right, that what it is. Now, the last thing though, even though you have the particle is moving, but it has to move in the right direction too, for that particle to experience the magnetic force. So that means the direction of the traveling is important as well. Okay, so we're going to have to combine these all requirements into how to, sort of the formula or the expression that eventually tells you what is the size of the force due to the magnetic field. Okay, so the magnetic field turns out have the unit of Tesla. Okay, so it's the same name as the electric car company there. All right, and of course you can derive it through the formula that you're going to see in a second here, but that's the unit for the magnetic field. Okay, here we go. The next one will reveal the size of the field in the unit of Tesla that we're talking about. Just give you sort of a sense of how strong the magnetic field is. So I think the best way to compare is just on the surface of the Earth, the magnetic field is somewhere around here, like 0.5 times 10 to the negative 4. So that's around us right now. Okay, we are sitting here. There's a magnetic field around 10 to the negative 4. And then, of course, if you have a bar magnet, that is like 100 times stronger, approximately. The one that you can pretty much like play around in sort of a scientific lab or something like that. But if you going to do like MRI, when you do like a medical imaging and all this stuff, the magnetic field go up to about like a one-digit number, like 1, 2, 3 Tesla. So that means 1, 2, 3 Tesla is a very strong magnetic field. Okay, that's super strong actually. All right, so what we are dealing with in our everyday lives is pretty much somewhere around 0.01, 0.001, somewhere around there. Okay, all right, so just give you like a rough estimate of the number. Okay, here we go. So this is what we have to deal with. And I think in the final exams, all you need to understand is just about here. Okay, all right, so we're gonna try to get right to the final as much as we can. So the key is this: there will be some sort of notation that we need to agree on. First of all, it turns out the force from the magnetic field is always perpendicular to the field. This is the weird stuff going on here. Okay, unlike the electric field, that's definitely true. So when you look at this one, I think we start from the left figure first. Okay, the green arrow representing the directions of the magnetic field. So right now the magnetic field point to the right. Okay, and now let's look at the positive charge first. Okay, the negative charge will come toward the end very easily. So if the velocity of this positive charge is going upward over here, that's a red arrow pointing up. Okay, so that means right now the magnetic field is going to the right, the positive charge going up perpendicular to the field. It turns out, look at this, the force is pointing into the page. Think of it that way. Okay, all right. So the way to find that direction of the force is going through the right-hand rule. Okay, this is the stuff that we have to learn today. So the right-hand rule say you start with your forefinger, okay, point toward the B, all right, and then you curl your hand toward the V, okay, and your thumb will point toward the magnetic force. Okay, all right, so that will be the one that you have to deal with all the time. So in this case, your V is pointing up, so that's your red arrow, all right, and then the B is pointing to the right, that's the green, so you curl your finger down over here, so that's why your thumb point into the page. Okay, so that is your direction of the force. Okay, you guys with me, all right, forefinger up, you curl your forefingers toward the B, your thumb will point toward the B. All right. So if you do everything for the, using your right hand, that is for the positive charge. And if you're going to deal with the negative charge, you have two choices. You use your right hand, and then you flip the side toward the end for the negatively charged particle. Okay, so that would be good. Or for some of you might want to do is let's just use your left hand if you want. Okay, you can use positive charge. Using the right hand for the positive charge and left hand for the negative charge. That will be your choice. Okay, but still right hand rule. All right. Now, because we have to deal with three vectors that are always perpendicular to each other, that's why there is another notation that you might have to deal with. you can use these two symbol. If you have a dot, the dot means it's out of the page, perpendicular to the page. So in this case, if you have a dot, it's pointing out of the page. And if you have the cross means into the page. All right, so let's check quickly. So if I have a particle moving to the right, let's say positive, like this, which will be the direction of the force in this case. So if this is the velocity vector, positive charge coming in from left to right, what would be the direction of the magnetic field that acting on this positive charge? So forefinger toward, along the V, okay, because right now B is pointing out of the page. So we have to curl outward. So your thumb will pointing downward. You guys, yeah, very good, like that. Okay, cool. Okay, forefinger curl outward, right? Because toward the B that's out of the page. So your thumb is pointing down. So this will give you the force pointing down. Okay, cool. All right, so that's what, whoa, we have more people here. All right, very good. All right. It's like a, all right. So this slide will give you the whole sort of like conclusion about determining the direction of the force. All right, so that's it. There is another way. If you want, you can use the palm of your hand or the stuff, but I would say the convention is pretty much using your sort of curling your finger or the stuff. All right, but so I think I'm stick with the left approach. Okay, all right, forefinger point toward the V, all right, and then just curl your fingers toward the B. Your thumb will give you the direction of the force. All right, that's right hand rule. Very good. Now let's practice. All right, so if you understand this, will lead you to the question in the final. All right. Okay, let's try. The first case, all right, there is the particle positively charged travel from left to right into the magnetic field pointing into the page. The direction of the force would be which direction, guys? Okay, let me write it. Oh, sorry. There you go. Once it enters the magnetic field area, forefinger, okay, point toward the V, curl into the page, your thumb pointing up. So in this case, the force will be upward. Okay, cool. All right, try again. The second one, and try this. Okay, now it's negatively charged. Okay, the velocity is now to your left. The B is up. Okay, so that means your forefinger point along the red arrow, curl upward, so your thumb will point into the page. Okay. All right, but then this is negative. So you have to flip that positive direction, so it's out of the page. Okay, very good. So in this case, the force that acting on this one will be out of the page. Let me put a dot here. That's the magnetic force. Okay, out of the page. Okay, you guys with me? All right, get going. What about this one? Now the magnetic field point to the right. The velocity is to the left. So what will be the magnetic force? Very good, very good. All right. In this case now, it's like, well, Ajahn is forefinger point along the red, and now you want to curl your finger towards the green, but then because they are anti-parallel in this case actually, so you don't know which direction you want to go, right? So in this case, the force actually is 0. Okay, because the condition that we have already seen, the force due to the magnetic field is always perpendicular to the magnetic field. So that's first thing. But if you notice carefully back here, even the velocity vector also has to be perpendicular to the magnetic force. So conclusion that we have right here is these three vectors must always be perpendicular to each other all the time. Okay, so that means what you have in this case, now they are not perpendicular at all. And that's sort of pretty much you cannot make it perpendicular whatsoever. They are anti-parallel. So that's why there will be no magnetic force acting on this charge. Okay, sounds good? Okay, all right, keep going. What about this? What will happen to this sort of wire if there is current flowing according to that purple arrow. So what will be the force acting on this wire? What do you think? So when you look at this one, this one looks just like, of course, now we learn from circuits that every time there is a current flowing, it means there is a charge also flowing in that direction as well. Okay, so knowing the current is the same thing as knowing the velocity of the charge inside. So knowing the current flowing toward, in this case, like along the purple arrow, that means the charges also have the velocity in that direction. So what should be the force acting on this wire, you think? All right, welcome. Yeah. So once again, velocity, your magnetic field vector is pointing down. So you go ahead and just curl your finger. Your thumb points this way. Here we go. With me? Agree? Okay. So that means once you let the current flow in the wire will be pulled to your right away. So this is what actually happens in real life, actually. Okay, so that's pretty much give you the whole sort of examples of how to determine the direction of the magnetic field. Oh, sorry, magnetic force. Okay, last one, guys. This is it. Okay, let's look at the bottom. We have already done this. So when the magnetic field is into the page, the velocity vectors point toward your right. The force will be upward, right? Okay. Now, if you look at the right position over here, okay, let me highlight orange here. Now the velocity is up. If you do the right hand rule, your thumb will point to your left. So that means the force will be to the left. Okay. Now look at the black position over here, right there. No matter what you're doing, the magnetic field will give the magnetic force point. Do you notice something here? Perpendicular to the V all the time, right? Okay. And we learned back in the day, whenever the force is always perpendicular to the velocity, what kind of motion you're going to get? You're going to get a circular motion. You guys with me? All right. If you remember, there is a formula saying that if you have like a centripetal force, it will be equal to mv squared over r. Does it look familiar to you guys? From sort of physics 1, maybe? All right. So that is it. So that means every time you have the force always perpendicular to the velocity, you will execute a circular motion all the time. All right. So from that, it means if I know how to calculate the magnitude of the magnetic force, I will be able to give you the relationship between the radius of circle, the velocity, the mass, all this stuff. And that's what we're about to do right here. So we have already known how to determine the directions. Now the last business is what is the magnitude of this force. Okay. All right. Here we go. You have two choices. The vector notation or just a scalar quantity, up to you. Okay. So this one, we use two vector. Okay, let me emphasize by putting the arrow on top. Okay, so the right hand rule that we have done can be written in terms of the cross vector. Okay, the process of curving your fingers or the stuff, that is the process of doing the cross vectors. And now for the magnetic force, it turns out the size of the magnetic force can be calculated from Q, V, cross B. And then if you want to find the magnitude, we're going to do this magnitude of this. All right? Okay? And that lead you to this. So the magnitude of this magnetic force vector can be found from this expression right here. Okay, so let me sort of bring you back a little bit about the cross vector. I don't know, have you done this cross vector before? Maybe. If not, that's okay. Okay, so the mathematics of this one is if you have vector A times vector B, okay, and then you do the magnitude, it will be equal to the magnitude of A times the magnitude of B and then the sine of the angle between these two vectors. Okay, this is general. This is mathematics. Okay, and then we sort of take this sort of the operation of the cross product and bring it to the calculation of the magnetic force over here. So that's why over here, actually what you have here is the V cross with the V. So that means if you want the magnitude of this one, you take the magnitude of the velocity times the magnitude of the magnetic field, and then times the sine of the angle between these two vectors. Okay, but of course, because you want to calculate the magnitude of the force from the field, so you multiply by the charge. So that's the whole formula there. So this is it. Okay, and this gives you the sort of go back in this case. We have already seen that in this case you have zero force, and now you can understand through the formula why, because now the velocity vector is pointing to your left, magnetic field vector pointing to your right. So in this case, the theta is 180 degrees. You guys with me? All right, so that's why the sine of this is definitely zero, sine 180. All right, so that's why every time that you have the velocity vector parallel to the magnetic field vector, you always get no force because of this sine theta requirements. You at least need some angle. You need some angle with the field to experience the magnetic force. And of course, the maximum that you're going to get is, okay, let me highlight over here. So theta, oops, sorry, it will be equal to 0 when theta is either 0 or 180 degree, right? But then you're going to get maximum of this, which you guys know. Maximum of this one is when theta is 90 degree. So perfect. You're going to get the maximum force when they are perpendicular to each other. And if you come in with different angle, so you have to take the sine of that angle. Okay. All right. So that's pretty much clear up the whole thing. So in conclusion, to figure out the force, you just apply this mathematical operation over here. Okay. And to determine the direction of the vector, just do the right hand rule and you're done. All right. Now, let's practice what happened. All right. Okay. Give it a shot. All right, so I think if we try to do like maybe, well, let me see, like 2-3 problems like this and finish with the circular motion, you already get like one problem down for the final. All right, so today's lecture is sort of guarantee 2 problems in the final. So it's kind of worth it, guys. Thank you for coming. All right, so you get 2 problems here. I'll let you know at the end. All right. Okay, so you guys at home, all right, so once we're done with the lecture, I will list problem number 1, I mean, what is it about, number 2, but okay, just give you the topic of each problem. No, we're broadcasting, all right, so, all right, okay, so you guys from the Zoom, don't worry, you'll get the same information as people here. All right, okay, let's try this one. Just give like a quick sort of practice of those formulas. A proton, so when you see proton means it has a positive E charge, so that's no problem. Move perpendicular to a uniform magnetic field at the speed given, so that's good. So that will give you the velocity already there. Experiencing an acceleration, oh, all right, so that gives you the acceleration in the positive x direction. So let me sort of give you an x-axis. When its velocity is in the positive z direction, so actually it's moving up over here. So velocity is up, okay? But the force, acceleration, sorry. Acceleration is to the positive x direction. There you go. All right. Determine the magnitude and direction of the field. Well, John, that's no big deal. If you know the acceleration, it means you also know the force because sigma F equal to ma, right? So the force is going to point in the same direction as the acceleration. There's no big deal. All right. So let me put sigma F equal to ma. So what should be the direction of the magnetic field, guys? What do you think? The velocity is up. The force is to the right. So you think what would be the magnetic field direction? Okay, what do you think? In. Okay, if it's in, that means your forefinger has to be up and you have to curl your finger into the page. Your thumb will point to your left. That won't be right. So it has to be out of the page. Out. Yeah. Okay, cool. All right, got it. Okay, you guys with me? Okay, your forefinger is up. Okay, because you want your thumb to point to your right, because that's your force, right? Your thumb is your force. So that's why you need the magnetic field to come out of the page. Okay, you guys with me, yeah? Okay, so in this case, I have to say magnetic field is supposed to come out. So let me put the dot over here. There you go. Cool. Come on. Okay, forefinger point along the V, forefinger V. Curl your finger towards B. B, magnetic field. So because right now we don't know, right? You have two choices. It's either curl your forefinger out of the page or into the page. But because right now you want your thumb to be point toward your right. So that's why it has to be coming out of the page. Okay, all right. Okay, cool. All right, very good. That's it. So you say the direction is out of the page. Okay, now if you want the magnitude, that's fine. You say according to F, oops, sorry, we just need the magnitude. It's just Q, V, B, psi. In this case, you guys will notice right away, it has to be 90 degrees. Yeah, because the angle between everything is perfect. It's 90 degrees, so that's good. So in this case, the force is known. You just set the F to be mass times acceleration. And that would be the mass of the proton. You can put the subscript P if you want to. Okay. And Q is just E. So let me write it one more time here. Mass of the proton times the acceleration is going to be E, which is the electric charge, but it's positive in this case. The velocity is known. This is what you want to figure out. Sine 90 is 1. So you should be able to calculate the B very easily from there. Okay? All right. So mass is known, acceleration is given, electric charge is known, the velocity is given, so you should be able to figure out the B this way. All right. And once again, the mass of the proton and the charge of the proton is given, so you don't have to memorize anything. Okay, so that should be good. Okay, next, try again. Here we go. So this is an old style TV, which nobody is using it anymore. All right, but anyway, let's just look at the configuration over here. If you have an electron shooting out toward the screen in the front, which is along the x-axis that you see in that coordinate system there, and let's say that the magnetic field now is 60 degrees though, right? The magnetic field is not perpendicular to the velocity anymore. Calculate the force acting on this particle and the direction. Okay, what do you think? Try this one. Okay, so if you don't think sort of too complicated of the whole thing, just like follow the formula. Force is just the charge times the velocity, magnetic field strength, and the sine of the angle between the V and B. Okay, so in this case, all you need to do is just substitute the charge to be the electric charge. Okay, the velocity is known, no big deal. The magnetic field is given. Now you just put the 60-degree angle in there. Okay, all right, and that's it. You just be able to calculate the magnetic force this way. But the point of this is, a point of this problem is this. The reason that I try to show you this because the reason for the sine theta is here. Let me show you this. Actually, it's a vector, so that means I can always break this vector into two components, right? One along the x, one along the y. Okay. Once you say this is my b sine 60. And the one that's coming here is b cosine 60. So you see something here? And now you understand why I just only need the sine of the angle. Because this dude right here is perpendicular to the velocity vector. With me? The right-hand rule requires that I need the vectors to be perpendicular to each other. So that's why I only take the component of the B that is perpendicular to the V into your calculation. And I actually throw away this cosine angle because that cosine 60 is parallel to the V, right? It contributes nothing to the force. Okay, so you can imagine that actually you can pack these two B sine theta. In your head, it's like, oh, Ajahn, this is just the perpendicular component of the B. That's why you need the sine theta there, okay? And if the B is already perpendicular to the V, this automatically going to 1 when theta equal to 90. Sine theta is 1. So you don't need to do anything. It's already perfect. It's already 90 degrees. Or on the other hand, if they are parallel or anti-parallel, it's useless. It gives you no force. Okay? Because all you need is the perpendicular components. All right, you throw away the parallel components. You don't care. Okay, very good. So that's sort of give you the whole picture why we need the sine theta for your calculation. Okay, so far so good. All right, let's do one more. And I think we pretty much done with this. Sort of figure out the force from the field. Now you have an electron is accelerated through some voltage from rest and then enter a uniform magnetic field. What are the maximum and minimum value of the magnetic force that this particle experiences? Whoa. So this one is you get the you get the voltage difference, you get the potential difference, and you drive it to move and shoot it into the magnetic field. Okay. So first of all, this delta V eventually will give the velocity to that electron. So you guys with me? Okay. All right. So that means, first of all, you drive that electrons with the potential difference first. So what I can do over here is I can just use simple conservation of energy, Q, or I can use E right now. E times delta V is going to be 1/2 mv squared. You guys with me? Simple. Okay, you guys still remember this just changed the potential into kinetic energy. Okay, all right, so that's done. So this one is no problem. So you should be able to figure out the velocity from this acceleration. Fine. So that's one is good. Now the question is, once you drive this velocity of the electron into the magnetic field over here, what will be the maximum magnetic field that you will get? Well, Ajahn, that just according to this, the magnetic field can give you the magnetic force equal to the charge times the speed, the size of the velocity, magnetic field, and the sine of the angle between V and B, correct? But you want the maximum. Of course, for this to be max, sine theta, it just has to be 1. Is that right? So that means you just shoot the electron perpendicular to the magnetic field. That's your maximum force. And this will give you the minimum when sine theta equal to 0. So that's it. This is just to confirm that the maximum force you will get when everything is perpendicular. And the minimum, don't have to think very much, 0, nothing. When you shoot it parallel or anti-parallel to the field. Okay, cool. Okay, so that's it. So I can answer max is just EV times B. And the minimum is just 0. Done. All right. Very nice. Okay, once you have this, here we go. When I say here we go, mean that's the hint of something is happening in the final exam. All right. Okay. Now, I'm going to combine them into the calculation of what is happening when the charge is moving inside the field. because the force always perpendicular to the velocity, that charge will execute a circular motion. Okay? And because it's so easy now, because the force and the velocity are already perpendicular, and the magnetic field right now is also perpendicular, so everything is perfect. So the magnetic force is just QVB. You guys with me, yeah? Perfect, right? Sine theta is 1. Okay? All right? So I just substitute the centripetal force with that QVB. Equate that to mv squared over r. I can cancel 1v out. Then, this is how I can calculate the radius of that circular motion. And from that, you can calculate whatever you like. For example, if you want to figure out the omega, the angular velocity, it's just going to be the velocity over r from v equal to omega r, something like that. Okay. Or if you want to find the period of the motion, you just take the circumference of a circle divided by the speed of that movement. You get how long does it take to complete one loop, one round, if you want to. So that means once you know everything like this, you can calculate whatever you want from the circular motion that you have done before. But for our final, I think it's somewhere around here. Somewhere around here. Very good. All right, very nice. So that's it. Let's give it a shot. A proton is moving in a circular orbit, given the radius 14 centimeter, given the magnetic field, which is perpendicular to the velocity of the proton. That's very nice. What is the speed of the proton? All right, and actually, if you look at the formula sheet, this formula is already in there. Okay, so that should be good. So you can just execute that one right away. It's a mv over qb. And because it's a proton, the charge is automatically one electric charge, electronic charge. So I can just say the v is just r e b over mass of a proton. And you're done. Okay. And of course, in the final paper, you just calculate the number for me a little bit. Just don't leave it here. Okay. But that is just punching the calculator now. Should be very easily done. All right, very nice. Somewhere around here. So this is a direct application of that formula, R equal to mv over qb. Okay. All right. One more. Okay, an electron moves in a circular path perpendicular to a uniform magnetic field with the magnitude given. So that gives you the magnetic field. That's a B. If the speed of the electrons is given, so that's good, that will be your speed. What is the radius of the circular path? And now part B, a little bit harder. What is the time interval required to complete one revolution? So actually this question is asking you to figure out the period of the movement. Okay? All right, let's give it a shot. So this one, you say, you want the radius R equal to m times V over QB. Okay, we got that one. The mass is just electron, so it is the mass of the electron. The velocity is known. The charge is just one electronic charge. The magnetic field is also known. So you should be able to figure out R from here right away. Okay, so this one is good. So part A is fine. Okay, so that's it. Map. That's done. Okay, what about part B, guys? You want to know how long does it take to complete one revolution? Because eventually what you have right here is you're going to execute one circular motion over here. Very good. It just takes one complete cycle. So the distance that you're traveling is just going to be 2 pi r, right? And then all you need to do is just divide it by the speed of that movement. Distance over speed, you get the time. That's it, done. ออกประมาณนี้โอเคไหม This is good. Very nice, yeah. Everyone, okay, done. That's approved. Okay, guys, I think if you sort of get up to this point, you should be able to do problem 11 in your final exam. That's kind of nice, yeah? Okay. Problem 11 about this magnetic field calculation, magnetic force calculation, and the circular motion of the charged particle inside magnetic field. Very nice. ครับผม No, pretty much just the calculations. Yeah, pretty much. Yeah. All right. Okay, very cool. All right, guys, this is good. This is good. Very nice. Okay. All right. So the reason that I like this problem because it's the one application that you can use from this one. I think this is very good. All right, and I think it's common in industry at this point. So look at this one. Because of R equal to mv over qb, correct? Okay, so this is a cool application now. And the machine that running this system is very expensive. I think it's a couple million baht. Yes. Okay, so look at this one. If you have a particle, okay, that coming in with some velocity, so let's say you know velocity is fine. And somehow, if you are able to charge that particle with some known value, for example, you might just put like one electronic charge, maybe +1, +2, -1, -2. So let's say that you know amount of charge in that particle. And of course, magnetic field, you should be able to tune it whatever you like. You can adjust your magnetic field and everything. So that means you can calculate the radius of your circular path, right, from this formula. And the nice thing about this one is, if you have a source with multiple masses inside, and then you let them run through this magnetic field, of course, they are all going to execute a circular path, right? But now you can see the R will be proportional to the M because you already sort of keep your other variables fixed. So the nice thing about this one is the radius of that circular path will eventually reveal the mass of that particle, right? And this, we named it the mass spectrometer. This one is the machine that actually let you sort of isolate isotopes from whatever particles that you want, how many types of isotope that you have in that element, for example. Or you can use this to analyze the components of your sample. It will shoot up into multiple circular paths, and then you can sort of pinpoint how many components in that in that sample. And you even know the mass of it, and you will be able to trace back what type of sort of particle that is, what kind of element that you have in your source, in your sample, and all this stuff. Okay, so this allows you to do like contamination detection, for example. Because if you run it through mass spectrometer and then somehow there is one sort of spectrum that coming out that you are not expecting that one, you might say that, hey, that sample is contaminated with something, or something like that. All right. So this is the very cool application of it's. That's why they say it's a spectrometer. So it gives you the components of that sample by separating the mass. Okay, so that's nice. And the cool trick of this is, okay, this one just for fun, all right, this one is not going to be in the exam, but you have a way to control the velocity very easily using everything that you have already learned up to this point. So you guys look at this one. I don't know you guys having fun with this or not, but just take a look at this. If I shoot the positive charge upward, okay, all right, shoot it up, and if I have the magnetic field point into the page, what will be the magnetic force acting on this? So you guys say, okay, 4 fingers up, okay, and then you call finger into the page, right? So that means your magnetic field will point to your right. That's your magnetic field. All right, give you the magnetic force. Now, if I say about, hey, everyone, I want this charge to actually going up straight. So I have to balance this force with another force. The way to do that is because this one has a charge in it. So what I can do is I can put think of it like a capacitor, yeah? So I have the positive plate on the left, negative plate on the right. So this will give the electric force pointing toward your right. So by having this, it means I can balance the force acting on this charge by using the magnetic force. This is QVB. Electric force is QE. You guys with me? All right. And now the charge cancel. Actually, I don't even have to care about what charge is on this particle. But by having this in this configuration, I can tell exactly what should be the speed of this particle. And then you attach this one right here. Oh, sorry, too far. right here, there. So you can use this device to be the velocity selector. So you can pretty much tune your velocity of the particle, and then you shoot it into the magnetic field, into the spectrometer. Okay, so this is like a cool, well, techniques and all this stuff. All right, guys, that's pretty much conclude problem 11 in the final exam. Cool. All right, done. Nice. Oh, there is like one more. All right, this one, don't forget to try this, but there's nothing more complicated than what we have already done. Nice. Okay. Yeah, the reason that I put the DIY here because it may be too close to the final exam questions. All right, but it's somewhere around circular path and all this stuff. Maybe I speak too much today. Okay, all right. Okay, anyway, give it a shot. Okay, guys, so that's done for the main point of today's lecture. You guys just came in. What I said earlier before we start this lecture is just this, the first page. Here we go. All right. There are two main components of today's lecture. Okay, so it's just particle in magnetic field, that what we have just learned. And the other one is the law that allow you to calculate the magnetic field. And that law is called Ampere's law. That's it. If you can get these two done, I think we're done with the course. Sounds good? All right. Okay. All right, so everyone on Zoom, all right, up to this point? Okay, very good. All right. One, okay, very nice, thank you. All right, here we go. So that's done with the first half of the whole thing. Let's take a look at the second half. Okay. Guys, this is the portion that I'm going to skip. I think you guys will like it because originally I supposed to teach you guys this portion of whatever things that's coming out. Okay, let me flash through and you'll see what's about to happen. Okay, something like this. This is the problem that you saw before. Okay, the one that you determine the direction of the magnetic field. Yeah. Okay, and these 3 pages allow you to calculate the force, but not on the charged particle, but on an electrical wire. Okay, because these two are pretty much practically the same thing. Every time that you have the current flow, it's equivalent to having a charge with velocity, right? Same thing. If the current is flowing upward, it means the charge is moving upward. So there's no doubt. Actually, you can also apply the same techniques with the current carrying wire as well. Okay? But I think I'm going to skip this one because I have to pretty much derive this and that and blah, 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 blah. And you're probably not going to like it. All right. But give you an idea that actually I can turn this QVB, the one that we just learned, into a current form instead of the charge form of the equation. Okay, but just sort of don't worry about it. So this one just FYI, just so you know that in the case of the current flow, you can also calculate the magnetic force as well. Right? But I think it's going to take too much time for you guys to digest this one. And then at the end, you're going to get like one more formula to your whatever calculations, and it doesn't really help anything much. So what I'm thinking is just like, hey, if you know the formula, you should be able to calculate the force on the wire, just like another formula that you have done before. So this one you can skip. Okay. All right. So this one's good. All right. Don't worry about this problem about the current carrying wire. Okay. But you should be able to calculate, or I'm sorry, you should be able to determine the direction of the magnetic force, okay, using the right hand rule. Okay. So that should be good. All right. Here we go. Now the second half of today's lecture is the source of the magnetic fields and how can we calculate the magnitude of that field from the source. Okay, so it turns out this is kind of amazing in the sense that the source of the magnetic fields is the traveling of the charge. That's kind of weird. So what I'm saying is this. So if you have a wire without current, so of course nothing is happening. But once you take the current to flow in that wire, the compass around that wire will actually line up in a circular path. This is, we can detect this one from experiments, all right? And the first one who noticed this one is by Ørsted. He's just doing some demonstration in classroom or something, and then he has some wire with the current flow, and then the compass nearby just flicker, tick, 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 or something like that. So he just noticed that, hey, it has to do with the current flow. It seems like anytime that you have a current flow, there will be a magnetic field around. Okay, so that's the hint that actually the source of the magnetic field is the motion of the charge, or we can say it's a current. All right, and that's what this one is about. Now, because from this node observation, the direction of the magnetic field seems to come in a loop. So you will be facing another right-hand rule. So every time you have a current carrying wire, your thumb can represent the current. And now your forefinger will represent the magnetic field that looping around. Okay, so in this case, if you do this, your thumb pointing up, forefinger wrapping around, you will see that there will be a magnetic field rotating. It's not rotating, it's actually in the direction that is in the right-hand rule, right? This is, if you look downward, it's going to be counterclockwise in this case. Okay, so this is the conclusion. The current is the source of the magnetic field. Okay, cool. All right, now look at this one. If you can analyze this scenario, I think you get the sense of what is happening today. So now you have two wires with the current flow in them in the same direction. So let me call them I1 and I2. Okay. My question is, what is happening between these two wires? Okay, let's give it a shot. Okay, so it turns out what's happening, what do you think is it? Labert. Separating? Yeah. Ah, why? That's the question.
Both are in the same magnetic field, like North Pole, North Pole.
Ah, North Pole, North Pole. Okay. Almost there. It just not right, but almost there. The idea is very close. When you say North Pole, which direction is the North Pole? That's the question. Oh, I think that's a good thinking. When you say North Pole from this one, which direction should give you the North Pole? Where is your North Pole in this case? Here. So when you answer that the North Pole is counterclockwise, kind of tough though, because North Pole is like a position, right? It's coming at a point. So when you say North Pole is counterclockwise, seems like there is something spreading in space. So that will be a little bit too wide of the North Pole. When you have a North Pole, there must be like a squeezing into a point, and it's generating some magnetic field outward. All right, but the idea is very close. So the thing is this, the point of this question is to practice what is happening with the current generating the magnetic fields. Okay, so let me sort of give you an idea. Wait a second, there is a question, so we don't need to study these 3 slides that we just skipped. Yes, that is correct. Okay, yeah. All right, yes, yeah. Don't need to study. Oh, that sounds really bad. It seems like I did something wrong with the educational system here. All right. For the purpose of the final exam, you don't need to study that. Okay, but for the purpose of your knowledge, you should study that. Okay. Anyway. All right. So here we go. Let's start from the top wire, the one that having the current I2 flowing. Your thumb point to your left. Your thumb point to your left. Your forefinger wrapping around. So that means your magnetic field will pointing in this direction. You guys with me? Yeah. Okay. All right. So now the I2, the I sub 2 wire generating the magnetic field around. So the bottom wire will experience the magnetic field due to the upper wire. And if you look at the position of the bottom wire, the magnetic field is pointing outward. You guys with me? Okay, because magnetic field is just going to loop around here, in there, coming back here, and it's going to shoot out B2 in the position of the bottom wire. Okay, so that means in the bottom wire, there is a current flow to your left, perpendicular to the magnetic field, B sub 2. So now you can apply the right-hand rule that we just studied. Forefinger point toward the velocity, curl your finger toward the B, your thumb will actually pointing upward. Okay, so that means your bottom wire will experience the force upward. Okay, all right. Now let's do one more. On the other hand, the bottom wire will generate the magnetic field around it as well. Okay, so the bottom wire will do the same thing here. So there will be the magnetic field. Let me call B sub 1. You guys with me? All right, so the bottom wire will do the same thing. You do your thumb point towards your left. That's a current. Your forefinger wrapping around. Okay, so you're going to get the magnetic field point that and that direction around the bottom wire. Okay, so now in the position of the upper wire, the magnetic fields actually point into the page. Okay, and because there is a current flowing on the upper wire as well to your left, that's your velocity. Let me call this V2. Okay, so what will be the force acting on the upper wire? You do the same right-hand rule. Forefinger point toward the V, curl toward the B, your thumb is pointing downward. All right, got that one, guys? Okay, so there will be a downward force acting on the upper wire. So that means at the end, what is happening? When you send the current through these two wires in the same direction, these two wires will eventually actually squeeze themselves toward each other. All right, so actually it's attracting each other. That's what happened. Okay, so now you can try, if you send the current in the opposite direction, now you can guess what should happen. They're gonna repel each other apart. Okay, all right, so this is the direct effect from the magnetic field around the current carrying wire, and we use the right-hand rule to determine the force on the moving charge particle in the field. And that's it. That gives you the conclusion of what's happening here. Okay, so the last thing that we want to know is, hey, but Ajahn, how can we figure out this? How can we know what is the strength or the magnitude of the magnetic field around the wire? If we know how to calculate this one, we know how to find the magnetic field from the magnetic source, which is the current right now. Okay, let's try to do that. Okay, so this is what's happening. When you have a wire, we use sort of your thumb pointing towards the direction of the current, right? Now, if I sort of take that wire and loop them into a loop like this, what should be the direction of the magnetic field, guys? So you say, oh, okay, then every single portion of this one, there will be a magnetic field coming around like this, right? Oops, sorry, wrong direction. Going around like this. So all you need to do is just do your thumb pointing towards the current. Your forefinger will wrap around with the direction of the magnetic field. So you can keep doing this around the loop, around the ring. So you will see that the magnetic field is sort of like coming up on the top and then try to loop it back in, right, toward the bottom, like showing in this figure right here. But when you look at this one, and then if you forget the loop, the ring for a while, you will see that the magnetic field is sort of shooting up, coming back in here, and then just loop back toward the bottom, right? It looks like this, right? Somewhere around here. Yeah, look like this. So this shape of the magnetic field that come up toward the top and then just loop around the bottom and come back here is sort of mimic or actually duplicate what is happening around the magnet bar. Yeah, it's like a bar magnet over here, right? Okay, so that means if you have a ring that's carrying a current, it will behave just like bar magnets. Does it sort of make sense to you guys? Yeah. So that's why if you have a loop that having a current flowing through, it will behave like a magnet. So that's why we can say this is an electromagnet. So it's a magnet that having the electricity running inside. You can generate a magnet this way. And where have you seen this electromagnet, guys? Have you seen this around? Of course, you see it from, I don't know, we have it here. The door, the one that you have like then you have to use like security when you have like the card that you tap on it and it just boom, you hear the sound boom. That boom actually is just cutting off the current flow. Okay, so that means all the time the door was closed by using the electromagnet. So you apply the current flow through, and then it's just having the magnet attach the door to whatever the locking mechanism. And then when you put your card into your whatever access card into your reader, and if it's allow you to enter, it just cut off the current. All right, and then you hear the ting sound, and then you can enter the building, all this stuff. Okay, so that's where the electromagnet is applied right there. Okay, sounds cool over here. All right, so in reality, this is what you need to calculate. And look at this equation. How do you feel? All right, very good. This is the worst, actually. This is even worse than Gauss's law. This is the, if I were to teach this one, this is going to be the highlight of the course. It would take like hours just to complete one problem. But I put it here just to give you a feeling of what actually needs to happen if you want to calculate the magnetic field from a current source. Okay, this is the equation. And the name of this one is Biot-Savat's law. I don't know, have you heard of this one? But I don't think so. It's kind of like coming very late. And it's even have the cross product in here. Whoa. Come with a little bit of differential stuff in there. Supposed to be. And then, of course, once you get that one down, you have to sum them up for the whole wire. Who would want to do that, right? Nobody wants to do that. But this is the thing that you need to do. After a lot of stuff going on here, really a lot of stuff, the final result is this. Isn't that nice? When I say isn't that nice, because we are not going to use this law, the Biot-Savart law, to calculate the magnetic field from an electrical wire with the current flow through. We will have a better choice of doing this one. So this one, to answer your questions, yes, skip. Don't worry about this one, okay? Just so you have a chance to see it, the name. Actually, seriously, I don't even know why I put this slide in here, right? Well, Ajahn, instead of skipping, you just get rid of this slide altogether. It will be easier. No, just want to show you a little bit. All right, here we go. So that means if we were to do the Biot-Savart law, this is about to happen. You just have to slice this into a tiny piece with the current flowing, and you calculate the magnetic field at point P. That would be the neat magnetic field there. And then you keep doing this. Calculate the magnetic field there. Slice, one more slice. Magnetic field there. Keep slicing, keep slicing, keep slicing. And then you sum everything from the left end of the rod to the right end of the rod. That's what you need to do. Okay, that's from calculus. And of course, for this one, because we are not trying to do any wire, we want to do like a super long wire, you can assume that the left end of this one going to negative infinity, and you can go all the way to positive infinity there. Okay, right, and we are not going to do this because look at the result. It's very clean. It looks so clean. Why I say so clean? Look at this one, guys. The results just saying that the magnitude of the magnetic field depends on two things. First, what is the strength of the current, right? How strong your current is flowing, which makes sense. The stronger the I, the stronger the field. That makes perfect sense. And the second one is how far away from that wire, right here, which also makes sense. If you are far away from the wire, you should have a very small magnetic field strength, right? So that's good. But it's just a matter of the factor in the front that just pop up. But other than that, that makes sense. B is supposed to be proportional to the current and inversely proportional to the distance from the wire. Okay, so we are going to get to this result using another law, which is much simpler to try, and we call the Ampere's law. All right, guys, the last stuff that we're going to learn in this course right here. And the Ampere's law, stick with that right-hand rule thing. So when you have the current flowing outward, we already know that you use your thumb pointing in the direction of the current. Your forefinger will give you the direction of the magnetic field around. And we actually know the result from the previous page, that the magnetic field equal to mu naught, some constant, times the current over 2 pi distance. Let's take a look at the Ampere's law. All right, here we go. Okay, let's give me 5 minutes to give you the idea of the Ampere's law. You guys still remember Gauss's law? Okay. In the Gauss's law, when you have a charge, electric field coming out of it, right? Coming out of it, right? So we say that those electric field diverges, it's diverge, coming out. But when you study magnetic field, it doesn't have that characteristic. Have you noticed? The magnetic field doesn't want to diverge out because of always have the north and the south pole side by side. So it doesn't have the sort of diverging characteristic, but it has sort of like the looping characteristic instead. Yeah, make sense? So that's why in the magnetic field, usually you will deal with the loop of the magnetic field, not the bursting out of the magnetic of the field lines. It's a circular pattern of the magnetic field. So this is what is happening. The magnetic field seems to go with the loop, not the divergence of the field. So in the Gauss's law, what you did was you're doing the surface integral because you want to calculate the flux, right? Remember, you want to know how many lines that actually penetrate through your surface. That was the Gauss's law, all right? And the flux calculation is one of the problems in the final exam. All right, that's one more hint. But anyway, I will go through one by one anyway at the end. Okay, so in here, we do not do that anymore because, well, there's no divergence of stuff. So it's pretty much useless if you want to do the flux calculation. So what you do instead is a line integral. You want to loop around with it. You want to go along with that loop. And you want to calculate like, hey, what is going on inside that loop? Okay, sounds good? Okay, so this is the something that is happening is you want to start with the loop and you imagine your own loop just like you imagine your own surface back in the day of the Gauss's law. นะโอเคเนาะตรงนี้จะเป็นอะไรที่ไม่ค่อยเข้าใจนิดหน่อยนะตรงนี้ so the idea is you come up with your own loop and you try to calculate how much of the magnetic field is actually right along your loop. Okay, and Ampere says whenever you calculate that right along the loop thing, at the end you will get your calculations equal to the amount of current going through your loop multiplied by some constant. That's it. This is the Ampere's law. So the Ampere's law still have the same features as the Gauss's law. That the right-hand side, that is your source. You guys with me? In the Gauss's law, the source is the charge. So in the Gauss's law, you put charge over epsilon naught, if you remember, on the right-hand side. In the amperes, the source is going to be the current. So you do the current and a constant. But in the constant that you are using right now is magnetic constant. So it's a mu naught instead of epsilon naught. Okay, so the right-hand side is still the source. Now the left-hand side, instead of having the flux calculation, okay, now you turn it into the loop calculation. So you want to know how much of the magnetic field actually going along your loop. That's what you're trying to do. You want to sort of like, hey, I'm going to follow this loop, and I want to know how much of that magnetic field components riding along the loop with me. So this is the key of the Ampere's law. Sounds good? All right. So this process of calculating this component of the magnetic field along the loop, we call it a line integral. Okay, but don't worry, we are not going to try to do crazy loop thing. The loop that we're going to do is going to look very simple, just like a circular loop. So your calculation will be a very simple line integral like this. Okay, let's follow my idea over here. So let's look at this one, guys. Because I can imagine any loop I want. And all I care about is how much current is flowing through my loop, right? Okay. So if I want to do the line integral along whatever loop that I'm doing, the right side of the equation will look mu naught times the current through the loop. So let me show you what I'm saying here is, you guys look at loop A. If my loop A look like this, the red loop, okay? And if I do this line integral thing along this loop A, my calculation, here, let me put A over here, B dot ds will be equal to what? I'm saying it's going to be equal to mu naught times, look at this. There is 1 ampere shooting towards you, 5 ampere shooting towards you, and 7 amperes shooting away from you. You guys with me? Okay, look at this. There is a 1 ampere shoot towards you, 5 ampere shoot towards you, and 2 amps shooting away from you. So the net current is going to be, if I say towards you is positive, let's see it that way. So it's going to be 1 plus 5 minus 2. With me? And that's it. It's going to be 6 mu naught. And you're done. Okay? So the key is you just only need to count the amount of current through your loop. So let's try again. Just give you one more example. If I only pick the D loop over here, whatever you do within that D loop will be equal to mu naught times, you have 5 towards you and 2 away, so your net will be just 3 amp. Yeah, okay, that's simple. And I can go even crazier. If you look at this one, if I do this loop right here, look at the loop D over here. What should I get, guys? Loop B, what should I get? B on the right, I mean on the right figure. Of course, 0, because there's no current through the loop. With me? All right, so that's it. So the Ampere's law is just as easy as the Gauss's law on the right-hand side. It's just saying that all you need to do is just count the current flowing through your loop. Just like what you did before with the Gauss's law, you just count the amount of charge inside your Gaussian surface. Same idea. All right. But for those of you that just like, well, Ajahn, what about to happen is going to get complicated? No, because I'm only going to use this result and showing you this. Okay, I'm going to do just the case of what is happening around the wire. And I think we will be done with this. Almost there, guys. Stick with me a bit. So let's look at this. I have a current flowing in the wire, okay, I, over there. Now I say that, hey, around this loop, there will be a magnetic field around. So what I'm imagining is just, I'm going to create a loop. This is my imagination, loop number one. That is my Amperean loop. That's it. That's my Amperean loop. Okay? And I assume that there will be a magnetic field around this. Around this. The reason this magnetic field is around because of the right-hand rule. We say that every current flowing, there will be a magnetic field looping around all the time, right? By the right-hand rule. So what I want to do is I'm going to calculate B, this is my magnetic field B, dot with my displacement along my loop, which is just that tiny piece of the distance along my loop, I'm just going to slice them into a tiny displacement along the loop. You guys with me? Yeah, so that's ds, 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 ds. Right here, ds. Okay? However, because everything is riding, sort of like circulating around the loop very nicely, so from the look of this one, B and ds are parallel. You guys, can you see that? Because it's just tangential to the loop. Okay, if you zoom it in here, see? The magnetic field looping around, that's your B. And of course, the displacement vector is always be tangential to the circle all the time. So that means on this loop, the vector B and the vector ds always parallel to each other. All right, right, okay. So that means I can say it's just B ds cosine 0. That's from the dot product. Okay. Every time you have vector A dot with the vector B, it's just AB cosine theta. But because they are parallel, it's just cosine 0. And now I assume that because you are at the same distance from the wire, the magnetic field should have the same strength around the loop. So that means I should be able to pull B out from the integral. Yes, yes, yeah. All right, almost there. What is the integral of ds, guys? I have the ds, 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 and just sum them up. It's just the circumference of a circle. Very good. So this integral is just 2 pi r. Okay? Very nice. So now I am arrived at B times 2 pi r. I'm done on the left side of the Ampere's loop, Ampere's law. I'm going to equate this with the mu naught times the current going through the loop. How much current flowing through the loop? It's just I. Okay? And now I can move 2 pi r to the right. That's it, guys. Done. Okay? So this showing you how can we get to that stuff that we skipped. Crazy thing from the integral, blah, 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 blah. Eventually, we can arrive to this result by using the Ampere's law. Okay? But the Ampere's law has its own complications in the sense that you have to evaluate the line integral a little bit. But for the case of sort of simple current in the wire, the Ampere's loop is just a circular loop. So you can do a line integral really easily. And then you arrive at this result. And I think that served my purpose. You know how to calculate the magnetic field around current carrying wire having the current flow I in it. And by just knowing this, you should be able to do problem 12 in the final exam. And that's very good. All right, cool. Okay, this application actually can bring you through calculations of the magnetic field around other things. Okay, for example, In this case, there is something called solenoid. You just take that wire and curl it into like a multiple loops configuration, and then you can calculate the magnetic field using this as well. All right, if you want to. Okay. All right. But anyway, I'm not sure you like to do this or not, but I will show you just for the sake of, showing you the Ampere's law and the power of that Ampere's law. I'll give you an idea. So this is a cutaway view of that solenoid. Okay. So what I can show you quickly is this, because I can assume that the magnetic field is supposed to be just within that solenoid. Okay. So this is what's happening. So we can assume that the magnetic field outside is kind of weak. So we can just like ignore that for now, just to make things a little bit simpler. So I'm going to focus on the magnetic field that's already inside here. That's what I'm trying to show you. Okay. So what I'm saying that, okay, let's assume that inside the solenoid, there will be a magnetic field just within that wire itself. So I'm just creating an Ampere's loop. Okay, let me highlight blue here. Here we go. All right, so what I'm going to do is I'm going to do the integral b dot ds, just like before. Okay, and because right now my loop composes of 4 sides of my circular shape of the Ampere's loop, so it's going to be side number 1, side number 2, side number 3, and side number 4. All right, but now you can see right away that because the magnetic field is only within here, see? The magnetic field is only within this region of here. So first of all, the area number 3 will go to 0 because there is no magnetic field right there. Magnetic field is gone, so that shouldn't have anything. Now, when you look at the side number 2 and side number 4, well, hey, Ajahn, okay, that outside has no magnetic field, so that should be no problem. It's go to 0 for sure. Okay, but inside right here, the magnetic field is pointing upward, but the ds that you're having is going to be 90 degree with the b. So every time you do the 90 degree dot product, b dot ds will be cosine 90. So it will give you 0 anyway. So what I'm saying is side number 2 and side number 4 will give you 0 integral anyway. So at the end, your line integral will be left just only the side number 1. When you look at the side number 1, it's just like, oh, Ajahn, the ds is going to be parallel to the b. Very nice. So that means your integral on side number 1, it will be b dot ds. And it's just going to be b ds cosine 0. Very nice. Cool. Okay. And once we have this, because we assume that the magnetic field is supposed to have a same size, same magnitude along the side number 1, I can pull b out from the integral. Cosine 0 is 1 already. I'm left with just the integral of ds on the side number 1. What should be this integral? Just like before, you just take the ds, and sum them up. So eventually, you're going to get just the length of that side number 1. Yeah, it's just a sum of the ds. So that means this, it will give you the length L. Okay, sounds good. So far, so good. So that means your integral will give you just b times L. And now you equate this to the right-hand side. You just say the mu naught times the current inside this loop. The only thing that you need to know is, well, Ajahn, I only have to count this, this, right? You just have to count how many wires that you are looping inside that Ampere's loop. So let's assume that I have number of this wire to be, let's say, n in here. I don't know how many, right? You can count them. And each one give you the current flow of I. So all I need to do is just put that n and I times. That's it. That's how simple it is. Each wire gives you the one current I. If you have n of them, you just have n times I. And that's it, guys. Magnetic field is just mu naught, number of wire, current flow divided by the length of that portion of the Ampere's loop. And then you can actually squeeze this tool in. This is just the number of lines of the loop per unit length. I can just keep it simple as this one, and you're done. That's it. So that means for the solenoid, it makes sense. If you want a very strong magnetic field, all you need is very high current. Yeah, that's for sure. And you need to have a very high density of that wire. If the density is very high, then the magnetic field will be strong as well, which perfect. Okay, sounds good? All right, so if this is sort of give you an overview of what the Ampere's law is sort of helping you to evaluate the magnetic field, that's it, guys. It's done. Okay, let's take a look at one example. Okay, this one we clear. We know how to arrive to this this formula, no problem. Okay. Okay, this one, don't worry about it. I don't think you will need to do this if you don't want to accelerate any particle or anything like that. So, but anyway, this is a nice shape. We call it a toroid. Okay, and you can use the same Ampere's loop. So this one I will give you like a DIY, but I don't know how many people want to try this. Can you get right to the problem in the final? All right, but anyway, I'll show you. I have already shown you what's done, what should be done in the solenoid case already. Okay, so for the toroid, you can try it at home whenever you like have a feel to do it. All right, guys, that's it. So when I say that's it, I can tell you right away. I think I'm missing a page or something. No, okay. The final exam rely on this expression right here. Okay, there. This is it. That's what we want. Okay. The key is, and let me give you one more time. Conclusion. If you have a current flow, I, okay, out of the page, okay, out of the page, out of the page, there will be a magnetic field around at the distance r, according to the right hand rule, of course. Your thumb point towards the eye, your forefinger wrapping in the direction of the magnetic field. So if the current flowing out of the page, your magnetic field will flow counterclockwise. Okay, sounds good. All right, so the magnetic field at any point will be tangential to that. Any point, tangential to that. And now you will be able to calculate that magnetic field strength directly by using this formula right here. That's it, guys. Done. This is what you need in the final.